we on? Okay, great. All right, we are now going to start the first of the 5 techniques that we're going to use in order to determine if a series converges or diverges. We're going to learn 3 of them today because they're all fairly simple algebraically, and then we're going to do the last 2 next day because they're also very, very similar algebraically. So the first one we're going to do, it's called the integral test. I have posted notes, especially if you're not really a good note taker. Now, the integral test basically means I'm going to compare the results of my series to the results of an integration. And the results of the series and the integration will not produce the same values, but they'll have the same trend. Meaning if one diverges, the other will diverge. We're going to prove that. And if one converges, the other will converge. Most everything we do, we're going to be looking for asymptotic kind of behavior. In other words, a series is going to act like something we already know, and that's for the conclusion of convergence and divergence. And here's the really important thing. If something diverges, it diverges. It's never going to add up to something finite. But if something converges, we can use technology to help us get a numerical value that's accurate to as many decimals as you need without knowing exactly what the right answer. So in other words, if the right answer were square root of 2, and we were incapable of coming up with that as an answer, we could still come up with as many decimals as you need. You're never going to look at the decimals and say, oh, that came from this number. That's not necessary. So the idea here is I have a couple conditions that have to be true. So I have the following series. Now, every time we do a new test, there's assumptions we have to make. The series has to behave in a certain manner in order to use that particular test. So in this case here, first of all, we're going to start with a series where all of the terms are non-negative. 0 is not negative, but 0 is not positive. And the reason is because the behavior of the series must be a certain thing. So we're going to start with something where every term, right, all the way forever and ever and ever, A1 is bigger than A2 is bigger than A3. That means the terms are getting smaller. Okay? You notice which way the inequality goes. Right. This means the terms are getting smaller. They can stay the same, but they're getting smaller. They're never getting bigger. And they're all non-negative. The reason is the negatives affect the integral part when I actually want to integrate. I need them to be all above the x-axis if I'm thinking of an integral. Okay? Now with that said, here's what I want to think of it like this. I'll put some numbers down. So let's just say this is A1, this is A2, this is A3, right? This is A4, this is A5, this is A6. You guys kind of see what's going on. They're getting the A's are getting smaller. So what I want to do is, if I thought of it like this, let's think of a function out there. Let's say f of x is such that f of 1 equals a1, f of 2 equals a2, and so on, f of n equals an. Now, the function can take real input. But if we input the numbers 1, 2, 3, 4, 5, and so on into the function, they're going to yield the exact same values. You with me on that? So that means my function is going to pass through all of these guys here, on its way this way. It's non-negative. I'm never going to dip below. I can approach the x-axis, but I'm never going to dip below it. And it's definitely going downhill. So that's the picture I have. The dots represent the actual value. So I'm going to add A1 plus A2 plus A3 plus A forever, never, 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 never. But what if I look at it from the integral standpoint for a moment? So here's what I'd like to do. I'd like to make little rectangles. Let's see, I want to go like this. Notice this rectangle has width 1, and this rectangle has height A2. So the area of that rectangle is equal to A2. Everybody agree with that? And then I'm going to do the same thing for the next one. And I'm going to do this all the way down the line. I'm not going to do all infinity of these because that might take a while, but that goes forever, never, 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 never. So if I add up the terms of the rectangles, okay, if I add up my rectangles, I'm actually starting at A2, aren't I? So the rectangles in my picture are starting at 2. Is it clear that that is definitely less than the integral of f of x that's going from 1 to infinity? Now stare at that just for a moment there. Can everyone see that there? The area under the blue forever and ever and ever would be the integral from 1 to infinity of f of x. And my rectangles are clearly less than that. Okay? Do you notice I started with that guy as my top one? I could do this differently, couldn't I? What if, I'm going to take the same problem. What if instead I went, you know what, let's go with this one. Let's make A1 the top rectangle. And then do the same thing this way. And then the same thing this way. And so on and so on and so on and so on. Now all of my rectangles are above the curve, aren't they? But I also started at A1. What do you think? Is this a true or false statement? That's possible. True or false? When I start at 1, it's bigger. By the way, is it a lot bigger? No, but it's bigger. That's all that really matters. Now, here's the crazy thing. Let me go off to the side. Isn't this simply this sum minus the first term? Does everyone see that? So let me rewrite this one here. I'm going to erase this stuff on the left. We're almost done, and it's such a beautiful, simple thing that we're about to conclude here. So if I said to you, an1 minus the first term, that's exactly what this is. That is definitely less than the integral. But that integral is definitely less than this, isn't it? It's going to be a little bit tight. Okay, can everyone see that right there? I really want a situation where I have the summation in the middle. Right now, my integral is between the summation minus the first term and the summation itself. Well, if I add the A1 to this term right here, okay, then wouldn't it be the case that this is the last thing we need to write? To these two terms, if I add that, that's a true statement. Agreed? But we already know that this is smaller than this, so that means the integral also goes here. And this is so cool what we're about to have here. I have just proved to you that if I have a summation where my terms are all non-negative and they're getting smaller, that's not outrageous. That's going to actually be probably the most common one we deal with at first. My terms are getting smaller. They aren't necessarily approaching 0 yet. They're just getting smaller and staying non-negative. I have just proved then that that infinite sum that we're looking for is between the integral and the integral plus the first term. And by the way, the first term is always finite, and the first term is 0. Wow. And so here's the simple thing. If the integral converges, then the sum will converge. Because the sum is between the integral and the integral plus the first term. If the integral diverges, then the sum will diverge for the same reason. Now, does that make sense? That's what I'm saying. That's beautiful. Now, whoever figured this out, that was extremely clever, I thought, right? Depending on which way I look at my rectangles. So the integral test says that if I have a series and I'm trying to figure out convergence and or divergence, but the argument that I'm looking at can easily be integrated, that's the thing. I have to be able to integrate it. Then I can use the integral test to determine convergence or divergence. It doesn't tell me what it converges to, right? It gives me an inequality that I'm between two values, but that's okay, because I can always do other things to figure out what it converges to. So let's do a really simple problem. Let's say this is the problem. We're going to do this particular problem 3 times today, by the way, because this one's so beautiful. Here's my series. So if I replace n with 1, then it's 1 over 1 squared plus 1, then 1 over 2 squared plus 1, then 1 over 3 squared plus 1, forever and ever and ever and ever. Okay. I would like to know whether this converges or diverges. So we will use, what do you think we should use for f of x? And by the way, if you want to call it f of n, that is fine. A lot of people don't like f of n because, you like integrating x's. You don't like integrating n's. That's so much harder, right? I say that jokingly, but no, it's totally uncomfortable if I use a different letter of the alphabet. It actually, the only thing that matters is that these letters are the same. Use whatever letter. But we generally use n's with the sums. We like x's with the integrals. So what am I going to use as my function? Anybody?
1 over x squared plus 1.
1 over x squared plus 1, yeah. I'm going to use that. I'm using the exact same function. Why? Because f of 1, f of 2, f of 3, f of 4, and so on will match the terms of the series. The difference is this is continuous. So this would produce an area, right, which is not the same as the sum, but we know it's going to be relatively close. So if I use this, then the problem I want to solve is this one. This is why you just learned improper integrals, because this is going to be a very common thing that you're going to do. All right? Now, that integral either converges or diverges. So right now I'm going to tell you, if the integral diverges, then the series diverges. If the integral converges, then the series converges. And that's what we're going to do. So, how do I start this? Well, it is an improper integral, so there can't be any infinity anywhere along the way, only in the final answer. So I'm going to do a limit right off the bat. Let's say as t goes to infinity of 1 to t. Now, this is not a scary integral at all, is it? Do we know the antiderivative? What is it? Inverse tan. Yeah, this is a happy one. So I have the limit of, is it inverse tan from 1 to t. Oh, inverse tan, actually, I think that's all we need. I'm going to put brackets around that. A lot of us want to take the limit now. Well, I can't take the limit yet because there's no t there. You're not taking the limit of x. So this would be the limit as t goes to infinity of inverse tan t minus inverse tan 1.
Right.
Is that right?
Right.
Now, I love the first one. And many of you did this, and you showed me, and I think this is what you just turned in today.
Yeah,
isn't it?
homework.
Yeah, you just did that. And a lot of you came to me earlier, and I like it because you told me what to do without me having to tell you. I love that. So just off to the side, a reminder. We know the tangent y equal tan x looks like this. And something we learned as baby algebra students, whenever you're doing an inverse graph, you just basically flip the graph over the line y equal x. So these asymptotes are x equal plus or minus pi over 2. Then these horizontal asymptotes are y equals plus or minus. And then the graph, that's the graph of the inverse tan. So as x grows without bound, I have a horizontal asymptote. Remember, limits in general, going back to Calc 1, a limit is finite, it's infinite, or it's a DNE. If it's infinite, that means it was growing without bound, positively or negatively. But if you get a finite limit, that means in every single situation like this, you had an asymptote. Not removable. I'm talking limits to infinity, not limits, as x approaches 1. Limits to infinity can only be finite if you have a horizontal asymptote. Y equal 1 over x, right? Approaches the x-axis. So that's my horizontal asymptote. Sometimes we forget. We learned that one when probably, well, if you're in my class, third day of the semester, that's one of the very first limits you learn because they're so nice and easy to work with. So because this is a horizontal asymptote, I know that limit is going to be what? Pi over 2. So this is pi over 2, and what's inverse tan of 1? It's pi over 4, so my answer is pi over 4. Does that mean that the series equals pi over 4?
No.
No, there's an inequality. What is the first term? When n is 1, what's the first term?
1/2.
1. No, 1/2, yeah.
1/2. Hang on one second. I gotta silence that. There we go. That's my ESPN updates. I don't know why it's so loud, but yeah. So if the first term is 1/2, here's what I can say with absolute certainty. I don't know what the sum is exactly, but I know what it's between. What's the lower end?
Pi over 4.
And what's the upper end?
Pi over 2. Pi over 4.
What did you say the first term was? We just proved this. This is the entire conclusion. This is the integral test in a nutshell. Can you tell me what the sum is? No, but it's between pi over 4 and pi over 4 plus 1/2,
Sorry.
which is finite. That's the whole point. I don't need the total. I don't need a number, because if I really needed a number, I would just have a computer do a simple do loop. What do you mean? Well, I just say for I equal 1 to give me a large number, do, add them up, and that gives me a reasonable number. That's it. So the question is, does this converge or does it diverge? What's the answer? Converges, and we always say it like this. This converges by the integral test.
Okay.
You always indicate which test, and I mentioned this last day and I want to make it really clear. Every time you do any one of our tests, there's going to be a number at the end of the line. There's going to be a numerical value. We're going to be finding a limit every single time. But the value of that number changes in its importance. Sometimes that number will mean that my series converged. Same number might mean my series diverges depending on, I did a different test. So you always indicate which test because, for example, this is a small finite number. Cool, this is easy. But in some cases, maybe that means my series diverged if that was the number I got at the end of the line. So by this particular test, everything worked wonderfully. Now, the integral test never should be your first option, ever. Because it is the longest of all of the tests. No matter what, it's the longest because you have to change the original problem into an improper integral and then go through those stages. Doing an improper integral is more work than the other tests usually. The other tests all involve taking limits, but they don't involve integrations, okay? What if the integration itself was really taxing? Well, then I might not be able to do it. A significant number of the problems we look at, you wouldn't be able to integrate. But if I can integrate them, so let's do another one. Let's consider this problem here. I started at 2. Why did I start at 2? Why didn't I start at 1?
Because ln of 1 is 0.
Yeah, that would present a problem. Yeah, your first term can't be undefined. And we mentioned this last week. The starting point cannot affect convergence or divergence of the series. The starting point can only affect what it converges to. Let's just say hypothetically that this series converges. Well, if I started at, let's say, 10, then this is going to converge to a slightly smaller number because I just lopped off a whole bunch of positive terms. Agreed? But that won't affect whether it converges or diverges. If this series diverges and I decide to start at 1,000, It's still going to diverge because I lopped off a finite number of terms that is a finite total. So convergence or divergence has nothing to do with what's happening early. We did an example of that last week, if you remember. We looked at something that got really big and then eventually got really small. That's the idea. So I am going to use f of x equal what? Make sure we do the right thing.
1 over x element?
1 over x log x. Oh boy, that's exciting. Well, maybe it's not bad. So now let's consider the integral from 2 to infinity. If I went 1 to infinity, then I have two different problems. One is I got to do a limit for the infinite part, but then a limit for the discontinuity at the bottom, and that's way harder. I don't want to do that. So this one here, then, the limit as t goes to infinity of 2 to t, all right? Now, let's concentrate on this problem here. And there's a dx there. All right. That one doesn't look trivial. So off to the side, if I had this, is this a u substitution?
Yes.
What would your u be?
Log x.
But u's in the denominator. That's not important. But if I let my u be log x, then what's my du?
1 over x.
And do I have that sitting around in the problem?
Yeah.
Yes, I do. Oh, so what does this become?
1 over u.
1 over u du, and that's pretty nice. That integral looked very scary, but the 1 over x is the chain rule factor, and it's part of the problem. If it helps you, maybe write it like this. So it's 1 over u du. Okay? So the antiderivative of this, just log u plus c. Nice. So that's log of.
Log.
And by the way, this is in absolute value because the log x can be negative, can't it? Can be negative. Now, will it be negative in this case? No, because we're starting at 2, but in general it could have been. So, going back to here, this will be the limit as t goes to infinity of the log of x, and because we're bigger than 2, let's see, well actually no, because log 2, yeah, this is okay. Log 2 is positive, right? It's just small. Or no, actually log 2 is negative. Yeah, so I need to do this. Okay. And then 2 to t. This is kind of a goofy looking one, but it is correct. So now I have the limit as t goes to infinity of the log of t, which is growing, minus the log of 2, which is finite. Just for fun, on your calculators, I want you to, let's have t be, let's have some fun. T is 1 billion. I want t to be 1 billion. So now, find the log of t on your calculators. We're going to put a really, really big number in there, okay? Anybody got a number?
3.0.
But that's obviously infinitely large, correct? You just did the log of 1 billion and you got 3. That's pretty small. In fact, if I did the log of something astronomical, way beyond that, it's still going to give you a really small number. But no matter what I put in, those numbers are always getting bigger. So this ain't moving very fast, but it's still
Moving.
This is still going to be infinite. Just for fun, I mean, put something, I'd say use scientific notation here. So let's do just, we might as well have some fun with this one. I want, not 1 billion, I want your t to be 10 to the 1,000th power. You can't even comprehend a number that big. Well, no. I'm going to do the log of 10 to the 1,000th power. Come on. So now what is it? The log of 1,000 log 10. Okay. we're going to do the log of 10 to the 1,000th power. I mean, that's a number sort of beyond reckoning. So what do we get here? Log. Well, obviously that's astronomical, that's error. That's about 7.7. It's still not very big, but it's still bigger. And it's going to keep getting bigger and bigger and bigger. If you're in a hurry to diverge, you probably don't want this series. But it does diverge. This is still going to be infinite. So this series diverges by the integral test. It's going to take a while. So again, hopefully you're not in a hurry. We just went out 10 to the 1,000th, and we only got a number that was 7.7 something. But if I put 10 to the millionth, or 10 to the 10 to the 10, you'll keep going, have some fun with that. You're going to keep getting not ridiculous numbers, but they are always going to get bigger. Now, integral test is a tool. It is never going to be your first choice because it's more work than the other ones. But there are problems that there is no other way to do it. This would be one of them. There's no other way to answer. There's no technique that we're going to learn that would handle this one. I always remind people, okay, L'Hopital's rule, you can do limits without L'Hopital's rule on almost every limit that exists. Every one you can do algebraically. Every trig you could do. The exception, I said, was exponential and logarithmic functions. Only L'Hopital's rule will work, and I have to rewrite them right as quotients. But if I have logs or exponential functions, there's no algebraic tool that I can use in the other way. I know the limit of sine x over x as x approaches 0. I know that limit. Therefore, I can use that to do most any of the trig limits. I know how to work with degrees, and we've manipulated things all over the place. But with logs and exponentials, you have to use L'Hopital's. Well, it turns out integral test is similar in that way. If there's a log involved, you probably have to use integral test most of the time. Because the tools that we're going to learn really won't apply to this one. Now, one of the most important and commonly used series that we're going to do, we're going to look at next. And this is a tool, you're going to like this one. Consider the following 1 over n to the p power. No coefficients involved, just n to the p. We have a very clever name for this one. It's one of the most common ones we work with. You'd never figured this one out. We call it a p series. Yeah, that was the best we could do. Makes it really easy to remember. A p series is anything of this form exactly. So 1 over n squared, 1 over the square root of n, things like that. Now, we already know, this guy diverges, right? I'll put, we did this last day. So if p equals 1, this diverges. We know that. The question is, can you give me a general rule that applies to all p series? In other words, if p was 3, what does it do? If p is -2, what does it do? If p is 1/2, what does it do? So that we can do right now with an integral test. So if I do the integral test, but in this case, p is not going to be 1. Because if p is 1, then the antiderivative is a logarithm. I want to do the general antiderivative for all exponents other than 1. Well, what happens with 1? Well, we already know the result. We already know it diverges if p is 1. So let's assume p is not 1 for a moment. So we can figure out every other case. Okay? Well, first thing I probably want to do, well, I'm going to do 2 things. The limit as t goes to infinity, and how about if I write it as x to the -p? Might make it easier to work with. What is the antiderivative of that? Well, it's x to the -p plus 1, or 1 minus p if you want to write it that way. And then what goes in front? 1 over 1 minus p. So far, so good. Let me put this in front. Now I have x to the 1 minus t. Let's see, and then I have what? I'm sorry, I'm not x to the 1 minus, sorry. T to the 1 minus p, look at that, didn't look quite right, minus 1 to the 1 minus p, which is just 1. T is growing without bound. Does that mean this is going to be infinite? Well, it kind of depends, doesn't it? What does it depend on?
It would depend on the value of p.
More importantly, it depends on 1 minus p, doesn't it? Whether it's
Greater or less than 0.
positive or negative, exactly. Oh, okay, let's look. We have two possibilities here, do you agree? We have two possibilities. 1 minus p is positive or 1 minus p is negative. But 1 minus p is not equal to 0 because we started by saying p was not going to be negative, or excuse me, p was not going to be 1. That would cause a problem, wouldn't it? P is not 1, so you agree I only have two possibilities. Let's start with the second one. What if p is less than 1? You know, p is a half, p is a third, p is negative 2. What if p is less than 1? Then that means that this exponent is positive, and this is growing without bound, therefore the result of this would be? The integral would be infinite. Diverges, but it's infinite, agreed? What if p is bigger than 1? Then that means that this exponent is negative, which technically means t is downstairs.
Negative.
And that quantity would be rapidly approaching
Negative.
0. Not negative, 0. If your denominator is growing without bound, your quotient's approaching 0. Oh, and so what am I left with then? This times negative 1, which would be the same as just saying 1 over p minus 1. I think we found the line in the sand. We already know this diverges if p equals 1. We did this last day. What if p is bigger than 1? Like n squared, n cubed, n fourth.
Then we get 1 over p minus 1.
Well, then the integral gives me a finite number, which means the series will
Converge.
But if p is smaller than 1, then the integral is infinite, which means the series will diverge. And by the way, yes, diverge to infinity, but diverge is good enough for now. Yeah, everybody cool with that? So the line in the sand is simply the number 1. So the p series will converge if p is bigger than 1, and it will diverge if p is less than or equal to 1. And that's a very, very powerful tool. Extremely powerful tool. Okay? Because we're going to use that one a lot. Does this sound kind of familiar? Remember the infinite painters?
Mm-hmm.
Wasn't it the same line in the sand? Go back and look at that one. Wasn't it the same thing? So we actually did this problem before, didn't we? Oh yeah, I didn't really need to do it again because we've already done it with the infinite painters. But the idea is a p series converges only if p is bigger than 1. But from that point on, I can just use that. Okay? Let's see. Now the next kind of series we're going to do, or the next test we're going to do is by far the easiest of all tests. But it also is the one you're going to use the least often because it has very strict rules. You can only have certain situations that you can use it in. But we're going to go over those situations. So if it's appropriate to use the next test, you want to use it because it's, again, the least amount of work humanly possible. The next one is something called a direct comparison, or the direct comparison test. Now, so let me give you a really simple example. Okay, last year I made a positive finite amount of money. I made a positive finite amount of money. In other words, I didn't lose money. Last year Gail made less than me, but it was positive. Okay. Does she converge or diverge? I made a finite positive amount of money. She made a smaller finite positive amount of money. So converge or diverge?
Converge.
Converge. I made a finite positive amount of money and Gail made more than me. Think of a number line. I'm finite and positive and she made more than me. Does that even suggest that she's finite? No, just that she's more than me. Can you make a conclusion? No, she's on the wrong side of the inequality. That's why I said it's very strict rules. Okay, last year, Austin made an infinite amount of money. It was a good year. And French made more than Austin. Can you give me a conclusion?
Yeah, diverge.
Well, leave the words converge and diverge out for a moment. He made an infinite amount of money, he made more. So he made an infinite amount of money too. Does that make sense?
Yeah.
Okay, Austin made an infinite amount of money and you made less than Austin. Could you be infinite? Yeah. Could you be finite? Yeah. Can I make a conclusion? No, you're on the wrong side of the inequality.
Okay.
So you get what after? If I'm smaller than a finite amount and still positive, then I have to be finite. If I'm bigger than an infinite amount, then I have to be infinite. But if I'm on the other side of the inequality, there's no conclusion that can be drawn. That's it. That's all you have to have in a direct comparison, is to be on the correct side of the inequality. You with me on that? So, let's consider, I don't know, how about this one? I'm going to walk you through a direct comparison. Direct comparison should be your favorite one because, again, it's the absolute least amount of work. You're not even going to take a limit in this case. Now,
Interesting.
look at my denominator. It's n squared plus 1. What do you think this is going to, well, doesn't it kind of look like that one? I'm covering up the plus 1. Does it kind of look like that one? And what do we know about this one?
That one's power.
Isn't that a convergent p-series?
Yeah.
So here's what I think. I think that this one is going to act a lot like the other one. They're not going to be equal, but they're going to be